Okay, so you remember everything we did in section 2.1, right?
Yeah.
Right before break, it's all still fresh in your memory. You went and reviewed your notes right before class. Yeah, that's what I thought. All right, so what did we do in section 2.1? In section 2.1, we had a handout. In section 2.1, we talked about second order linear equations. And we had a whole bunch of theorems. And so the theorems that said, like, if you had two solutions, then you could add them together and that gave you a third solution. Once you had two solutions, you could add them together, and you could even multiply by numbers and get a third solution. So once you had two solutions, you actually had how many solutions? An infinite number of solutions. And then we talked a little bit about linearly independent. What did linearly independent mean?
They weren't on the same line.
Not that they weren't on the same line, no. Linearly dependent means you can multiply one by a number and get the other. So linearly independent, that's what you were saying, it means you can't do that. So for example, like x and x squared are linearly independent. I can't multiply one function by a number and get the other one. And then what was important about linearly independent functions? We used the Wronskian to show that they were linearly independent. That's true. But the big theorem right at the end was if we had two linearly independent solutions, then what did we have? Then we had all of them. Once we had two linearly independent solutions, any other solution could be written as a sum of those two solutions. So that was really the big theorem. That was the thing we really wanted. What we're going to do today is we're going to do all the same theorems over again, except instead of having second order differential equations, we're going to have third or fourth or fifth or sixth. It doesn't matter how many derivatives we have. So we have pretty much all the same theorems. So I'm just going to show you the theorems. I'm not going to prove any of them. They're really all the same as what we had last time. So for example, this first theorem says, suppose you have a differential equation of nth order. So you have nth derivative. If you have n solutions, you can make a new solution. If you have n solutions, you can make a new solution by multiplying the first equation by a number, the second equation by a number, the third equation by a number, so on and so forth, and adding them all together. So that's the exact same theorem we had, except in section 2.1 we said, well, we only have a second order equation. If we had two solutions, we could make up a third. So now I'm saying if you have a fifth order differential equation, if you have 5 solutions, you can make another one just by adding a linear combination. The next theorem we had was a theorem that guaranteed solutions. And so this one says, suppose that P1, P2, Pn, and f are continuous functions on the open interval I containing a point A. Then, given constants, the differential equation is guaranteed to have a solution satisfying all of the initial conditions. And that's the exact same theorem we had as the other day, except we only had a second order differential equation, so we only needed 2 initial conditions. How many initial conditions will you need if you have a third order differential equation? 3. And if you have a fourth order differential equation? 4. So on and so forth. That's all this theorem is saying. If you have an nth order differential equation, you need to have n initial conditions. And once you do have n initial conditions, you're guaranteed to have a solution that matches those initial conditions. All right, so we talked about linear dependence when you only had 2 functions. What happens if you have more than 2 functions? What if you have 3 or 4 or 5? What does it mean to be linearly dependent or linearly independent? What did linearly dependent mean for 2 functions again?
Multiply by some factor and it'll be the same.
You can multiply by some number and get the same. Another way to say that would be I can multiply one equation by a number and then add the 2 equations and I can get 0. Right? for example, if I had 3x squared and x squared. Those are clearly linearly dependent. What can I multiply the one by to get the other? I can multiply this one by 3 to get that one.
I can multiply by 1/3 to this.
Or I can multiply this one by 1/3 and get that one. Or another way to say it would be, I could leave this equation alone, that function alone. I could take the second function and multiply by -3, and then they would add up to be 0. So that's another way to define it linearly dependent, is that you can multiply one equation by a number, add them together, and get 0. And that's the way we define it when we have more than two functions. So we say functions are linearly dependent if I can multiply the first function by a number, the second function by a number, the third function by a number, the fourth function by a number, so on and so forth, add them all up, and get the number 0. Of course, there has to be one little restriction, C1, C2, all those numbers cannot be the number 0. How come all those numbers cannot be the number 0? Because it would be cheating, because then it would clearly all add up to 0, wouldn't it? If all these numbers were 0, 0 times anything would be 0, and they would all add up to 0, so that wouldn't really say much of anything. Questions on that? We'll do some examples here in a minute of linearly dependent, linearly independent. Okay, and then we have the same theorem that we had. The theorem says if you have a bunch of functions and you compute its Wronskian, if the Wronskian turns out to be the number 0, then the functions are linearly dependent. If the Wronskian is not 0, then the functions are linearly independent. All right, but we do have a little bit of a problem there. When we talked about Wronskian, we did Wronskian for two functions. What was the Wronskian if you only had two functions? What was our definition? Anybody remember? The Wronskian of F1 and F2. How did we do that? We took the determinant of something.
Wasn't it F1, F1 prime, F2, F2 prime?
F1, and then where did F1 prime go?
Under F1.
It went below F1 prime, F2, and F2 prime. What if we have more than two functions? What if we want the Wronskian of F1, F2, and F3? It's the determinant of what? A bigger matrix, that's right. You're going to have F1, F2, and F3 going across the top. What are you going to have in the second row? F1 prime, F2 prime, F3 prime. But in order to be able to take a determinant, the matrix has to be square. So if it's 3 across, it has to be 3 down, which means second derivative. You're going to have F1 double prime, F2 double prime, F3 double prime. So that's how you would find the Wronskian of three functions.
So like, how would the computation go? Would it be like F1 times F2 prime, and then, well, I don't know.
All right, so how do you find the determinant of a 3 by 3 matrix? That's a whole other question.
Yeah.
We'll talk about that when we do some examples.
Calculator.
Unfortunately, your calculator will not help because these functions are going to have x's in them. They're not just going to be numbers. Your calculator will take the determinant of a 3 by 3 matrix that only has numbers in it. Your calculator will not help you with these problems. TI-89 would help, or a TI-92, that's true. But a TI-83 or 84 doesn't do you any good for finding Wronskians, unfortunately. All right, so we'll get to that in just a few minutes. And then here was the big theorem. This was the important one. This one says if you have an nth order differential equation and you have n linearly independent solutions, then you have all of these solutions. Any other solution can be written as a linear combination of the solutions you already have. And that's the exact same theorem we had the other day, except the other day we only had a second order differential equation, and we said we needed two linearly independent solutions. So basically, if you have a fourth order differential equation, how many answers do you need to find? 4. Once you find 4, and those 4 happen to be linearly independent, then you found them all. Questions on that?
It's still going to be as easy as just simple basic algebra.
In theory. The difficulty is factoring fourth degree polynomials can be very difficult. In fact, factoring third degree polynomials can be very difficult. So in theory, yes, it works exactly the same way. In practice, it's much harder. We have a quadratic formula which allows us to solve any second order polynomial. There is a cubic formula, that's true, but I don't know what it is. There's actually a fourth degree formula.
I saw the third and it took up an entire page.
Yeah, the third one's long. There's one for fourth degree. I don't know what that one is either. The bad news is if you get above fourth degree, fifth, sixth, seventh, there is no formula. In fact, it has been proven that there cannot be a formula. So there's a quadratic formula, there's a cubic formula, there's a quartic formula. Quartic, fourth power. Beyond that, there are no more formulas. And so solving gets really, really hard after that. Good news is, we won't go that high. In this class, we'll do second order, we'll do third order, but the third order, and maybe some fourth, they'll be fairly easy to factor, though. We'll see how those factor. So you don't need to program it into your calculator. Well, it would be very helpful to have the quadratic formula programmed in your calculator. If you don't have a quadratic formula program, I have one that I would be willing to share. I have a very nice one. It's very nice because it gives complex answers too, and we will need complex answers in this course. All right, so what we need to do from here, we need to do some problems. So I'm going to steal some problems out of the book. This is on page 122. I wonder if the black will show up better. And problem number 2. It gives us f of x is 5. G of x is 2 minus 3x squared. And h of x is 10 plus 15x squared. And the directions say, show directly that the given functions are linearly dependent. That is, find a non-trivial linear combination of the given functions that vanishes identically. Fancy words, I like that. All right, so what are they saying?
Make it equal to 0.
We need to add them up and make them equal to 0. So we need to find 3 numbers. So we need to find a number a, multiply that by the first function, so we're going to have a 5a, plus we need to take the second function, 2 minus 3x squared, multiply it by some number b, and then take the third function, 10 plus 15x squared, multiply it by some number c, and we need to make them all add up to 0. And a, b, and c cannot all be the number 0. At least one of them has to be not 0.
So if C is 1, B is 5, and A is negative 1, negative 2.
Negative 4?
Negative 4, yeah.
So you want A to be negative 4, you want B to be 1, and no, you want B to be 2, 5.
5. Yeah.
All right, so the bigger question is, how are you getting these answers?
Just canceling things out in my head.
Just kind of canceling out in your head. So what you're doing is you're actually doing a process called equating coefficients, and you didn't even know it. You're just doing it in your head. So here's,
fancy words.
I know, I like the fancy word. So here's what we do. We equate the coefficients. What I mean by that is I'm going to put all the things together that are just numbers. So the things that are numbers are 5a, and then I would have a 2b, and then I would have a 10c, and those all have to add up to 0. The numbers have to add up to 0. Then I would look for the things that just have x in them. But this one's fairly simple. What things have just x in them? No, not x squared, just x. Nothing. There are no x's, are there? So I don't have to worry about the x's at all. So then I look at the x squareds, and for the x squareds I would see negative 3bx squared plus 15cx squared equals 0. Or if I really wanted to, I could factor out the x squared, and I could just say that's really the same as negative 3b plus 15c has to be 0. And that's why it's called equating coefficients. We equate all the coefficients of the things that are just numbers. We equate all the coefficients of the things that had x's in them, but there weren't any for this problem. And then we equate the coefficients of the things that had the x squareds. What you normally end up with is a system of 3 equations with 3 variables. And you have to solve that system of 3 equations with 3 variables. Now the good news is this one's pretty easy to solve. You can do it by inspection. And that's what people were doing. People were kind of solving this one in their head and saying b has to be 5 and c has to be 1. And that'll make the x squareds go away, won't it? So b has to be 5, c has to be 1. And once you know that b is 5 and c is 1, that's 10 plus 10, which is 20. A would have to be negative 4 to make it add up to 0. So you're kind of able to solve that system of equations in your head. That's all you have to do for that question. Yep. Questions on that?
We should have a lot of those.
You should have a lot of those? All right. Well, let's see how clever you are then. We'll try another one. Number 4 has f of x equals 17. G of x is 2 sine squared x. And h of x is 3 cosine squared x. So again, what we really need to do is we really need to find 3 numbers a, b, and c. So that's 17a plus 2b sine squared x plus 3c cosine squared x adds up to 0. Oh, I have a question before we go on to this one. Back on that other one we had. Is that the only right answer? No. Can you give me another right answer? 4 and negative 5, negative 1 would be another right answer. Can you give me another right answer? If I were to make negative 10, make this one negative 10, make this one, if this one's going to be negative 10, this one has to be negative 2, and that one has to be positive 8. So we multiply them all by negative 2. So how many correct answers are there? There are an infinite number of correct answers. You ought to be able to find one of them, right? All right.
Thanks, George.
You're welcome. All right, so how many correct answers are there? There are an infinite number of correct answers. Anybody have one? It's weird because there's not like x's and x squares and numbers where you can equate your coefficients.
If we make b 3 and c 2, we can get a 6 out front of both of them, and we can get 6 times sine squared of x plus cosine squared of x. That becomes 1.
All right, so there's the clever trick on that one. What he said, I think he said let B be the number 3 and let C be the number 2. Because this would then be 6 sine squared and this would be 6 cosine squared. Why is that helpful?
Pull the 6 out.
You can factor the 6 out. Sine squared plus cosine squared is 1. So this is now, this whole thing is now the number 6. So what do I have to have A to be? Negative 6 over 17? Yep. A equals negative 6 over 17. So there's a correct answer for that one. And that's the trick on that one, is using the sine squared plus cosine squared equals 1. Questions on that?
So you can't always use that same method we did in the first one, where you just pull out the ones that have only numbers?
Right, that first method that we did in the first one, that works when your functions are all polynomials.
Okay.
Doesn't work, unfortunately, when you have other things involved. Trig, yeah, good old trig functions.
We're not going to do like any power reductions or anything like that with trig, right?
Not yet. All right, number 8, we go the other way. Number 8 says, here's 3 functions, f of x equals e to the x, g of x equals e to the 2x, and h of x equals e to the 3x. And it asks us to use the Wronskian to prove that these functions are linearly independent. So in number 4, we prove that these functions are linearly dependent. Number 8, we want to show they're linearly independent. So we compute our Wronskian. Our Wronskian has the functions e to the x, e to the 2x, e to the 3x. Then it has their derivatives. What's the derivative of e to the x? E to the x. What's the second derivative of e to the x? E to the x. What's the derivative of e to the 2x? 2e to the 2x. And the second derivative? 4e to the 2x. And then we have 3e to the 3x and 9e to the 3x. So there's our Wronskian. All right, does anybody know how to find the determinant of a 3 by 3 matrix?
Linear algebra people.
Linear algebra people. You haven't done that yet?
No, done it with I, J, and K on the top row.
And how do you do it with I, J, and K on the top row?
You get
Cross
an
out
answer
the top
of something I minus something J plus something K, which those somethings are the 2 by 2 determinants of the sub whatever it
And that's exactly what we're going to do here.
is. Okay.
That's what I thought.
All right, so to find the determinant, you need a sign chart. And the sign chart looks like this. It goes plus, minus, plus. And then the next row is minus, plus, minus. And then the third row is plus, minus, plus. You pick your favorite row or your favorite column of the matrix. The way you can determine which one is your favorite row or favorite column is if it has zeros in it. You always want to look for one that has zeros. Doesn't help us with this problem, does it? None of them have zeros. All right. So if none of them have zeros, personally, I usually just pick the first row. So you start with the first item, which is e to the x. And e to the x, that's position as a plus in front of it. Then what you do is you cross out the row and the column that had that e to the x in it. And you write down what's left. So what's left? It would be this little block down here, right? So I write down 2e to the 2x, 3e to the 3x, 4e to the 2x, and 9e to the 3x. Then I go to the next position. The next position is an e to the 2x. But in my sign chart, that one gets a minus. So that's going to be minus e to the 2x. And then I cross out its row and its column. Nope, because I used this one right here. I'm just going straight across. So there's the e to the x. That one's the e to the 2x. I cross out its row and its column. And I write down what's left over. I have an e to the x, are 3e to the 3x, e to the x, and 9e to the 3x. And finally, I go to the last position. The last position is an e to the 3x. In my sign chart, that's a plus. So plus e to the 3x. Cross out its row and its column. So I have e to the x, 2e to the 2x, e to the x, and 4e to the 2x. So notice what we did. We took a 3 by 3 matrix and we reduced it to having 3 2 by 2 matrices. How does that help? We know how to find determinants of 2 by 2 matrices, don't we? How do we find determinants of 2 by 2 matrices? We do the cross multiplying and we subtract. All right, so we're going to have e to the x. We multiply diagonally. That's going to be 2e to the 2x times 9e to the 3x. How much is that? 18e to the 5x. You add your powers there. Minus, we multiply diagonally the other way. 12e to the 5x. Then we move right across here and we keep going. Minus e to the 2x times 9e to the 4x minus 3e to the 4x. And finally, we have plus e to the 3x. Do our diagonal multiplying. 4e to the 3x minus 2e to the 3x. Almost done. We simplify everything. We have 18 minus 12 is 6, so that's 6e to the 5x, but then we multiply by x, we get 6e to the 6x. Then we're going to have a minus. That's 6e to the 4x, but we multiply by e to the 2x. That's minus 6e to the 6x. Finally, we have plus. That's 2e to the 3x, but we multiply by e to the 3x. That's 2e to the 6x. We get all done. We get 2e to the 6x. Is that a good thing?
Yeah.
Yes. Why?
Because it's not 0.
Because it's not 0. That's correct. When are these functions linearly independent? When the Wronskian is... That would be linearly dependent. Linearly dependent would say...
I got the question asked since the beginning.
Wronskian is 0. So we wanted these functions to be linearly independent, which meant we wanted our Wronskian to be anything except the number 0. And that's clearly not the number 0. So what if we'd done all that work and got the answer 0?
We messed up.
We made a mistake because the book said show that they are linearly independent. So,
What happens if 2 of the functions are dependent and 1 is not? What are the implications of that for our purposes?
that's an excellent question. Let's find out. So what he asked is, what if we have 2 functions which are clearly linearly independent? So give me 2 functions which are clearly linearly independent. X and 2x. Those are clearly linearly dependent, correct? And then we're going to throw in a third function. Give me a third function which is clearly different from those 2 functions. Sine x. Oh, that's a good one. All right, so clearly these 2 by themselves are linearly dependent. But what can we say about all 3 of them put together? Are they linearly dependent or linearly independent? How do we tell? We take the Wronskian. All right, so our Wronskian will be the determinant of, we'll have x, we'll have 2x, and we'll have sine x. And then the derivative of x is 1. The derivative of 2x is 2. I went the other way. Changed direction on you. And the derivative of sine is cosine. And then this works out really well. The derivative of 1 is 0. The derivative of 2 is 0. Negative sine. All right, so here's our sine chart. Okay, so if I'm clever this time, which row or column do I choose to find my determinant? I used the last one. Why? It's got 2 zeros in it. Why is that helpful? That's right. So my first one, I'm going to have 0 times I cross out its row and its column. But 0 times anything is going to be 0. And then I go to the next one. I'm going to have 0 times cross out its row and its column. That's 0. So the only one I have to do is the last one. That's why you look for the zeros. The zeros save you a lot of work.
You get 2x minus 2x.
So the last one we would have, it has a plus in front of it, but that's a minus. We have minus sine x. And then we would have cross out its row and its column, x, 2x, 1, and 2. So we get negative sine x times 2x minus 2x, which is 0. So what would that tell us? Those are linearly dependent because our Wronskian turned out to be the number 0.
So there's some way that you get from all of these.
That's right. They all three of them need to be different, basically, is what this is saying. If 2 of them are linearly dependent, the whole thing's going to crash. Peter.
Then how would you find that number that you need to make it more?
Excellent question. All right. So David's question is a times x plus 2b times x plus c times sine x equals 0. What should the numbers a, b, and c be? A is negative 2, b is 1, and c is 0. Remember, the rule was that they can't all be 0. We didn't say that some of them can't be 0. So in this case, we want c to be 0. That gets rid of that one. A negative 2 and a positive 1. It makes those two add up to 0.
Is there another answer?
Is there another answer? Sure. Let this be negative 4 and let that be 2.
Infinite, no.
Let that be negative 8. Let that be 4. Would you like me to go on? There are an infinite number of correct answers, just multiples of each other. And it always works out that way. There's always an infinite number of answers, just multiples of the original answer that you find. Other questions? All right. So, what's the moral of the story? The moral of the story is computing a 3x3 determinant kind of stinks, doesn't it? What if I was in a really bad mood and gave you a 4x4? You'd have to do it. You do the same thing, except your signs would go plus, minus, minus. They would just alternate. So you would start with a 4x4 matrix, and you'd have to do 1, 2, 3, 4 of them, and that would give you 4 3x3 matrices. And then you need to take those 4 3x3 matrices and reduce them each to 2x2 matrices.
Yes, but if we had any polynomials in them, by the fourth power, they probably.
Hopefully some of them might be polynomials, so that by the time you did your fourth derivative, you were down to 0. That's true. The moral of the story is you don't do that by hand. Grab Wolfram Alpha and you ask it to compute the determinant of a 4x4 matrix. You don't do it by hand. It takes way too long. So I wouldn't do that on a test or a quiz. That would just be way too mean.
That would be the only question.
It would be the only question, which wouldn't be particularly important.
You have to take it home and switch my program.
All right, the next problems. They look like this. This is number 14. It says y triple prime plus 6y double prime plus 11y prime minus 6y equals 0. So that's a third order differential equation. So how many initial conditions do you need? 3. And how many linearly independent solutions do you need? 3. So here are your 3 initial conditions. Y at 0 equals y prime at 0, which is 0. And y double prime at 0 is the number 3. And then here are your 3 linearly independent solutions. Y1 equals e to the x. Y2 equals e to the 2x. And y3 equals e to the 3x. The directions are: find a solution that satisfies those initial conditions. First off, what does the solution have to look like?
Isn't that like C1, Y1?
C1, Y1 plus
Plus C2, Y2.
C2, Y2 plus
C3, Y3.
C3, Y3. And that was our big theorem. Our big theorem says if you have 3 linearly independent solutions, any solution can be written as a combination of those 3. Now what we need to do is we need to find C1, C2, and C3 to match these 3 initial conditions. What does that mean I have to do? I don't have to do any Wronskians, but I do have to do some derivatives. I need to plug 0 into the original function. I need to plug 0 into the derivative. And I need to plug 0 into the second derivative. Alright, so I'll take my derivatives first and then I'll plug my numbers in. So y prime is going to be c1 e to the x plus 2c2 e to the 2x plus 3c3 e to the 3x. And y double prime is c1 e to the x plus 4c2 e to the 2x plus 9c3 e to the 3x. Well, I'm very glad they gave us 0, because what happens when I plug 0 into these e to the power things? They become 1. So I get C1, when I plug in y at 0 equals 0, I get C1 plus C2 plus C3 equals 0. And when I plug 0 into my second derivative, I get C1 plus 2C2 plus 3C3 equals 0. And finally, I plug 0 into my second derivative. I get C1 plus 4C2 plus 9C3, but this time it equals 3. I end up with a system, 3 equations with 3 variables. How do you solve a system with 3 equations and 3 variables?
Matrix.
You use your calculator and you use the matrix technique on your calculator. That is correct. I do not require you or expect you to solve 3 by 3 systems by hand. You can if you want to, but it's going to take you a long time. Alright, so how does my calculator work?
Matt said hit the on button.
I hit the on button. Alright, that was the correct first step. I hit the on button. Second matrix. And matrix is over here on this. Can't see that very well, can you? Well, you can't see it very well, but you have to trust me. Matrix is over here on the same button as X inverse. So I go second matrix. I go over to edit. I hit enter. I need my matrix to have 3 things down, but 4 things across, because I have the numbers 1, 1, 1, and 0. So you need to set it up so that your matrix is 3 by 4. Mine is already 3 by 4. If yours isn't, just type in 3, enter, 4, enter. You type in your numbers. Going across, I have 1, 1, 1, 0. Go across the next one. 1, 2, 3, 0. And across the last one. 1, 4, 9, 3. So you type in all the numbers. What do you do after all your numbers are typed in? You quit out of this. You go back to matrix. You go over to math. And you go down to RREF.
Wait, I missed that. You go second quit, you said?
Second quit.
Alright.
Second, back to your matrix button, which is the X inverse button.
Alright, then you go to math.
Go over to math. And you go down, down, down. I think it's letter B, maybe.
It's easier to go up.
It's easier to go up. You go down to RREF, which stands for
Reduce row echelon form.
Row Reduced Echelon Form. You had it right, just in the wrong order.
Yeah.
Row Reduced Echelon Form. I can tell who's been in linear algebra. And then we got to go tell it back to matrix. Use matrix A. You hit enter. And what it tells you is you have 1C1, 0C2, 0C3 equals 1.5. So that tells you that C1 is 1.5. The next row tells you C2 is -3, and finally C3 is 1.5. So there's your answer.
Oh, I see.
C1 is 1.5, C2 is -3, and C3 is 1.5. So our final answer would be y equals 1.5 e to the x minus 3 e to the 2x plus 1.5 e to the 3x. There is the solution that matches that differential equation with those initial conditions.
Wait a minute. I got like -0.3 and I got 0.15.
All right, well, there's only one way we could differ.
He's off by a factor of it.
One of us typed in some numbers wrong. And that's the only thing that can go wrong with these. So let's see, mine has 1110, 1230, 1493.
I accidentally put in a 9.
That'll do it. So that's the only mistake you can really make, is to type in a number wrong.
Yeah.
So yeah, can't see that very well.
Did we only go as far as taking the second y derivative for that one?
Yes, because we had a third order equation,
Right.
so it gave us initial conditions for the original y, the y prime, and the y double prime.
Oh.
So I used this equation here. This one came from y, this one came from y prime, and this one came from y double prime. So you only need 3. So I don't need a y triple prime to find the answers. Other questions? All right, the last thing in this section. There's one more theorem, and this is a new theorem. Up to this point, we've only talked about homogeneous differential equations. And what did homogeneous mean in Chapter 2?
Everything at the same time.
Nope.
Sorry.
That was Chapter 1.
It was 0.
In Chapter 2, homogeneous meant your differential equation equals 0. What if your equation is not homogeneous? Well, there's a theorem. And the theorem says, let y sub p be any solution, a particular, any solution to the non-homogeneous equation. If y1, y2, yn are linearly independent solutions of the associated homogeneous equation, then any other solution at all can be written as the solution of the homogeneous equation plus the particular solution. All right, so what does that look like in practice? Well, let's take this exact same equation we just had a minute ago. Y triple prime plus 6y double prime plus 11y prime minus 6y equals, instead of 0, I'm going to make it equals 12. If I want to find the solution of that equation, I need two things. I need to have what we call the complementary solution, which is the solution of the homogeneous, and then I need any solution to this equation as it is. Just a minute ago, we saw that the complementary solution to this, the solution of the homogeneous equation, was c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. So what I need is I need a particular solution. I need any solution to this original differential equation as it is. Can anybody give me a solution to that differential equation as it is? I'll give you a hint, it's a number.
Y equals 0. Well,
Y equals 0 does not work. Because if I plug in 0, I get 0 plus 0 plus 0 plus 0 equals 12. You're not off by much, though. If I plug 1 in, I get, what's the third derivative of 1? 0. What's the second derivative of 1? What's the first derivative of 1? So this is 0 plus 0 plus 0 minus 6 equals 12. So 1's not the right answer. Negative 2 is the correct answer. The particular solution is negative 2. So that tells me the general solution to this differential equation, I take my complementary solution and add, I should have just written minus 2, add my particular solution. That's what that last theorem says. Now, we have two very large questions we need to answer, and this is what's coming up in the next few sections. How do you find the complementary solution in general? We looked at that the other day, actually. We saw that we could solve a polynomial. So we'll talk more about that. And then the harder question is, how do you find a particular solution? If I were to simply change that to be 12x, I don't think we would be able to guess so easily and find the particular solution. And so that'll be a big section there, is how do you find particular solutions to these equations. So that's what's coming up in the next couple sections. How do you find the complementary solutions? And then how do you find the particular solutions? We'll work on that. Questions on anything?